So welcome to today's lecture, and today we will continue something that we started off last time. Actually, let me pull out what we did last time. Recent opinions, lecture.
Oh, by the way, Pranav, so this CA supports LaTeX. Uh, it turns out.
It supports LaTeX.
So you see
You
the
convert LaTeX.
you see the
Huh?
sigma symbol
Yeah.
beside T. Just press it.
Like this, huh?
Yeah. I mean, you should be seeing a pop-up where you can write LaTeX formula and it should convert.
Yeah. I saw that pop up, and it was already filled with X squared for some reason.
Yes.
X cadet.
X.
I see. Okay. Yeah. So I mean, we had stopped at the wiretap channel last time. This is just to refresh your memory. That yeah. So let's recall. So I mean, the wiretap channel is a point-to-point channel. So there is a legitimate sender Alice, legitimate receiver Bob. But the wiretap tells us that there is also a malevolent receiver Eve. Okay. Now Alice wants to send a message M to Bob. Okay. And ideally, Bob should decode the correct M with high probability. So hat M should equal M with high probability. But then Eve also gets some information about the message. How? So what can Alice do to send through a noisy channel? Of course, she will encode her message M into a probability distribution over the code words. Okay, so the channel has an input alphabet. So for every M, there's a probability distribution over the symbols X of the input alphabet. Then the channel does its work, and what it produces for every X, for every input symbol X, is a joint probability distribution on Y and E. So Y is the symbol of the output alphabet, which will go to the legitimate receiver Bob, but Eve is the side information that goes to the eavesdropper. Okay? And it's a joint distribution in general, Y and E. And since, of course, this X out here will depend upon M, so indirectly the Eve gets information about the message. Okay. And at the legitimate receiver's end, Bob, of course, gets Y, and he will pass Y through his decoder, which is a private coin algorithm, and it will output a probability distribution on messages hat n. Okay, that depends on Y. And this is it. And of course, we had the requirement that for all n, for all messages n, probability that the decoded message m hat is not equal to n is less than epsilon. So here the randomness is over what? Remember, this is true for all n. So the randomness is over the private coin encoding procedure. So this p x given n. Then it is over the channel randomness, which is p of y given x. And there's a private coin decoding procedure, which is p of hat n given y. Okay? So these are the source of randomness in this expression. And this should be less than epsilon for every candidate message. Okay? And the message M is just a number from 1 to 2 to the R, capital R being the rate. And the secrecy requirement is for all messages M, the probability distribution that Eve sees, so that will be P of E given N, it should be approximately equal to fixed distribution, independent of that. Okay. So let us say we take the marginal PE out here. And now our strategy is going to do the following. So let us say I fix a probability distribution of the input alphabet, and we'll analyze it for the input alphabet. Or we'll analyze it by optimizing over all input probability distributions, PX. The setup is clear so far, the channel and the requirements. Yeah. Okay. So now we want a procedure which gives us correctness, okay, correctness of decoding, and also secrecy against eavesdropping. Okay, let's go down. Yeah. So the strategy is fix a probability distribution on the input of px. Okay. Remember the channel characteristic p of y e given x is fixed. Okay. But what is in the encoder's control is this encoding probability distribution p of x given n. And what is in the decoder's control is this decoding probability distribution. Okay. Okay. So the strategy starts by first fixing some input distribution, okay, px. Then choose your code word. So I choose IID according to the margin on PX. So how many symbols X I will choose in IID fashion? Actually, 2 to the capital R plus small r. So in the noisy channel encoding theorem, I only chose 2 to the capital R symbols in the random code book construction. Here I choose more symbols. If I want to send 2 to the R messages, I'll actually choose more. I'll choose 2 to the capital R plus small r. But this code book, so this is my code book. I'll break it up into blocks. The blocks are of size 2 to the little r. So the number of blocks is 2 to the capital R. So each message now corresponds to a block. Okay? It's not, it doesn't correspond to an individual coder, but it corresponds to a block. And each block is of size 2 to the little r. Now to transmit message number n, Alice chooses the mth block. Okay. So let us say m equal to 2. So she chooses the second block out here and she sends a random code word from the mth block. So more formally, I mean, she chooses a random index k, which ranges from 1 to 2 to the r, and sends the kth code word within the mth block. So this is the encoding procedure. And let us see why this may work. So first of all, the correctness for Bob.
So small r is block size, right?
Smaller, yeah, block size 2 to the smaller.
Okay.
So Bob, okay, recovers the actual code word. So, I mean, Bob is truly speaking only interested in hat ends. Bob is only interested in the block number. But in our decoding strategy, we make block recover the actual code word also. Okay. So block recovers something more. Anyway, I mean, if he recovers the actual code word, he recovers the block number, so it's fine. And what does Eve see? Remember, Alice has chosen a random code word within the block. So this randomness is private to Alice. Okay. Neither Bob nor Eve knows it. Now, Bob actually doesn't care. Bob says that, I mean, even if you send one particular code word out here, I mean, he's going to recover it. And what does Eve see? Eve, the probability distribution that Eve sees is averaged over the mth block. So how do I say that? Remember, k is the index within the block. So here, this expression x 2 to the m minus 1 plus k just tells me that I choose the kth code word in the mth block. So for the kth code word in the mth block, I get a distribution on Eve's symbol, PE given x. Okay, and I average this probability distribution over the choice of the code word within the block. So sum over k, and then it's divided by 2 to the r. And what we hope is that this is close to the marginal distribution P. So what are the requirements for this to happen? So remember, like Px was the probability distribution input alphabet. Then there was a channel, okay, which for every symbol input symbol x creates a joint distribution y and e. So this is the underlying probability distribution, the control probability distribution, and under which we'll evaluate these mutual information particles. So Bob's correctness of decoding requires that R, capital R plus small r is less than I epsilon min from x to y under this distribution P. So, I mean, this in particular ensures that Bob can actually recover the code word. Okay, even more than the block name, he can recover the actual code words. Okay, this was the noisy channel coding. This was the packing argument. And to ensure secrecy against Eve, we require that this average be close to the marginal probability distribution. So this is the setting of the covering number. And this will be true if the sample size here is 2 to the little r, the block size, right? So little r should be larger than I epsilon max of between x and d. Okay? So this is the covering lemma, and this guarantees each secrecy. So what is the overall rate we get? The overall rate is r. So any rate r less than the difference of these two quantities. So what are the two quantities? I epsilon min xy okay, under t minus I epsilon max x. So of course, I mean, for the rate to be non-zero, this right hand side should be a positive quantity. If it is the case, then I can say that any rate satisfying this constraint is achievable. Okay. And in the asymptotic IID setting, what happens is take the same picture, okay, and repeat everything IID. Repeat the channel IID times. Okay. In fact, even repeat the encoder IID times. Okay. Only the decoder becomes a joint decoder, and then we know that the smooth mutual information quantities go to the Shannon information. I'm getting a call, so I'll just mute for a moment. Okay, yeah, probably spam. Okay, yeah. So we know that the smooth min and max mutual information go to the Shannon mutual information. So we get the Shannon mutual information between x and y minus the Shannon mutual information between x and y. And if this is positive, any rate R per channel use less than this quantity is achievable. So intuitively, what is this telling us? This is telling us that if the channel, let's go back to the channel. If the channel from Alice to Bob is less noisy than the channel from Alice to Eve, correct and secret communication is possible. Okay. So channel from Alice to Bob is less noisy means the mutual information between X and Y is larger than the mutual information between X and Y. It's a fairly natural quantity. I mean, if the channel from Alice to Bob was more noisy, then we expect that Eve will learn more about the message, no matter what we do. That fits in with our equation. So, any questions about this? This is where we stopped last time. Okay. Yeah, Hari. Last words for Yeah, Hari. Any questions?
Hello?
You're saying something?
It's fine. It's fine.
Yes, fine. Okay. Let us just go. Okay. So let's in fact let's just continue here. So let's okay, so now let us prove a converse. So let us prove. So we know that rate R less than so we'll prove a almost matching converse that any rate both correctness must satisfy reciprocity R less than okay. There was one thing I should maybe say. So of course, or actually, let me. So when I evaluate this, remember I had fixed and input distribution px. So of course, I mean, one is going to optimize over this px. So I will say that max over px, okay, of this quantity. The quantity being the difference of the two mutual information. Any rate less than this is achievable. So any rate, the converse will be any rate satisfying both correctness and secrecy must satisfy something like px of this quantity. We will see if the epsilons remain the same or they change slightly. Plus some order one. Okay. So now let's come down. Okay. Yeah. Okay. So what do we have? So remember, I mean, we had some encoder. So remember, this was M. Okay. This was coming from the encoder, and then we had this. This was the channel. Okay. And then we have the decoder. And what did we have out here? We had P of X and M. So any such encoding decoding procedure look like this, and this will be P of M hat given X. Okay. Sorry, given Y. And then this is another output. And we had this joint distribution P of Y E. Okay. So yeah. So now so what do we know? We know, and we are getting a rate R. So we know from the noisy channel coding theorem that R is less than, okay, max over Px. Okay. And what do we know out here? I mean, this is E, the eavesdropper E, right? I mean, if the secrecy has to hold true, then we know that P of E given M is approximately equal to some fixed distribution Q of E, right? Independent of it. So the same reasoning as the noisy channel coding theorem will say that the rate R is less than, okay, so what is this probability distribution Px out here? So think of it as the probability distribution Px induced by encoding procedure P of X given. And remember, PM is uniform. And PM. So then, any such protocol, because of the secrecy requirement, I mean, satisfies this constraint Px, and I'll get I epsilon min x colon 1. Right? 100. So is this expression clear? So this follows from the same as noisy channel, the one-shot noisy channel. Coding. Is this clear, Hari? So that the difference between the good old noisy channel coding was their R was less than max over any input distribution Px. Okay. Here I cannot take any input distribution Px. I have to take, yeah, well, I forgot to write that, of course. Yeah. So I have to take Px satisfying. I have to take Px such that PE. Remember, once I fix the input distribution Px, PE gets fixed also. Yeah, sorry. So PE given M is approximately equal to some Q. Sorry, not M, given X. Okay. So this is the difference between noisy channel coding converse without the secrecy constraint and converse with the secrecy constraint. Okay. Now, okay. Now the observation is that if probability of the probability distribution of E given the X, okay, actually, I shouldn't put in X. I think I have to just go back to X. Yeah. So let me write an M for now, and we will fix this later. This is not both. So we're getting used to this. Yes. Let me write this one. Now, the point here is that this Yeah, so claim that if the probability distribution on P is approximately constant, then I epsilon max x square. Yeah, actually, something like this. So this is the question. So let's prove this. Yeah. Okay. So what am I saying? if I'm saying that the probability distribution on E is almost independent of n, this means that so formally it means that P of probability distribution on M is probability distribution on M times probability distribution, some distribution Q. Okay. And so this is what it formally means, but that immediately implies probability distribution on M is approximately so maybe this is 2 epsilon Pn times P. Okay. Small difference between the two statements. So what am I trying to say? I'm trying to say that see this condition that probability distribution on each symbol E is independent of the message. Okay. So that was formalized by saying that this is this is epsilon close, okay, to some fixed distribution independent of any message. So formally speaking, that would become the joint distribution on ME is approximately equal to the margin on M, okay, times this fixed distribution Q on D. But now, if a joint distribution looks like this, then this tells me that the marginal distribution on E, PE, is epsilon close to QE. This is the data processing inequality for the L1 distance. So now by putting the triangle inequality together, so maybe the epsilon becomes 2 epsilon. Does this look like 2 epsilon? It's not 2 to the epsilon, it's just 2 times epsilon. Okay. So this is close to PM times P. So that's the first observation, that if you have the secrecy requirement, the joint distribution between the message and Eve's random variables is approximately equal to the product of the margins, epsilon close in L1. Now, once you have this, I claim that the following holds. Okay. So this implies that D to epsilon max P,
PME.
yeah, so PME with respect to PM times PE is less than or equal to 0, right? Because when I'm doing the optimization in the smooth max divergence. So I'll just perturb the distribution PME into PM times P. Okay, and then I'll get 0. Maybe the optimization gives me even something less than 0. Remember that the max divergence can actually be less than 0. Okay. I mean the smooth max divergence.
Basically, what is being said is that PM tensor
Yeah.
P is a candidate,
It's a
and the
candidate. Yeah.
actual optimizer drives it even smaller.
Yeah. The actual optimizer is going to be the same thing, but remember we are allowed to use subnormalized states, right? So the I mean you can make the total mass of the probability distribution 1 minus 2 epsilon or something like that instead of 1. Okay, so it will be a small negative number. Anyway, so we are just interested in this. What is this telling us?
What are we optimizing on? We are optimizing on PMA joint.
Well, oh yeah, so this is the optimization out here, right? So remember this by definition is the same as Dmax of some P hat ME, right? Yeah. Times P, and the condition here was that P hat ME is close to PM, right? In fact,
2 epsilon plus.
2 epsilon, yeah, 2 epsilon. In fact, there was an operator inequality. So let's not bother. I mean, the actual description of P hat ME is less than or equal to PME, which means the vector P hat ME is a vector of positive quantities, but they add up to something less than 1. So it's a sum distribution. And coordinate wise, it is less than the distribution PL. Okay, so we find such a P hat ME, okay, and we are optimizing it. So there is a certain, should I say, minimization. Okay, over P hat ME. Remember this, Hari? There was a minimization over P hat ME of Dmax. Dmax of this, right? So the what Shandon remarked is that I can take a candidate P hat ME to be the same as PM times P. Okay? That will already give me 0. Maybe the optimizer is even drives it negative. As I said, I mean, the usual optimizer will be P hat times ME, but you scale it down by something like 1 minus 2 epsilon.
Pranab, I have a question. So,
Yeah.
So this is true for even quantum states, as far as I can tell.
Yeah.
So doesn't that mean
Yeah,
that any two states or distributions, let's talk in terms of distributions, any two distributions which are not any two, maybe is for this form, that if a distribution PAB is close to PAPB, then doesn't that automatically give you an operator inequality? Oh, it gives you in
I mean,
terms of
I get the smooth max thing. No?
you get
The
the smooth,
epsilon.
yeah, you get the smooth max,
Yeah, exactly this. Yeah, that's all. Yeah.
But one cannot really remark anything about the non-smoothed thing, right? That can still blow up.
Right. Yeah, I mean, the before the smoothing, this may even have. I mean, you cannot say that the support. Well, in this case, it is true that the support of PME is contained in PM times P simply because it's a product of marginals.
Yes,
but
yes.
But more generally, I mean, there is no such requirement. Okay. I mean, it can happen that there's a teeny tiny probability coordinate here with a teeny tiny probability, but it's exactly 0. So, I mean, these two distributions are still epsilon close in the L1. Okay. But the Dmax is infinity simply because this has a coordinate where this is non-zero, maybe like something like epsilon over 100. And in that coordinate, this distribution is exactly 0. So these kinds of pathological things can happen. That's why smoothing is nice, when we remove these small quantities.
So doesn't this imply the opposite direction of Pinsker in asymptotic IID? Because the smoothed thing. So what does Pinsker say? That if you have at least in asymptotic IID, that if your mutual information is small, then your L1 distance is also small. So this is sort of telling me I'm going to use two things. The first thing is that in the limit, the smooth max approaches the mutual information, and the second thing I'm going to use is this observation. So that tells me in asymptotic IID, if two things are close in L1, if these at least of this form, that if they are close in L1, then their relative entropy is also small, or their mutual information is also small, which is the converse of ulta direction of Pinsker.
Yeah, so there is, yeah, you are right. I mean you can even prove that more directly actually. So I mean there is a converse of Pinsker for small trace distances, for small L1 distances. Yes. Okay. But yeah, but then I mean there are ifs and buts. Okay. So remember, so this is like the converse of Pinsker, but for smooth max. Okay. And
Yes.
yeah, and then I mean if you go to asymptotic IID, of course the epsilons blow up. So I mean you have to be a little careful. But it is possible under some circumstances to get a converse of Pinsker. Okay, so I think if you work it out, the size of your sample space, basically the support of the probability distribution starts being able.
Okay.
But, yeah. I mean, which is kind of like, I don't know, again, yeah, so there are advantages to working with the epsilon max. So we can usually avoid Fano and the size of the support, but then we have to pay a price elsewhere. There's no free lunch, of course. But at least in some cases, this makes it conceptually nicer. So the nice thing is this is kind of like a converse of Pinsker. Like if the L1 distance is small, then the smoothing. But remember, the smoothing parameter 2 epsilon is set to be the same as the L1 distance. Okay, so that's where the cheating is happening. So L1 distance here becomes a smoothing.
Oh, okay. So then in asymptotic IID that might blow up. Acha.
Yeah. Good. Any further questions? Hari, is this clear?
Yeah.
Yeah. Okay. So what have we proved? We have proved that if probability of E given N is independent of N, this probability distribution, then the smooth max information between the message and Eve is small, less than epsilon. Okay. So now we are almost done. So what is this telling me? Okay. So this is telling me that so my rate is less than max. Overall distributions Px. Okay. So remember, okay, so I mean there's the M also. So this there is this mapping from M to P of X given N. Okay. And P of E given M is something like QE. Okay. This is actually, yeah. So I mean now that I brought it out here, so let me not jump that. Let me just write this maximization over these strategies. And then this was, you should remember the proof of the noisy channel coding theorem. This was I epsilon min n y, right? And then we had a data processing inequality which said that the mutual information between message random variable and y is less than the mutual information between the input random variable x and y. Right? So there was the data processing inequality. So yeah, but I'm just going back to one step before that. It will help me in a moment. So now what we have out here, remember we want to wiretap, so we have the same maximization as before, all this blah blah blah. Now I'll write I epsilon min this is 2 epsilon max. Sorry. Right. Now, this is further less than. So remember this maximization had all these requirements that I am maximizing over mappings from the random, from the message symbol n to probability distributions over x. Okay, p of x given n. I'm maximizing over these kinds of mappings. But now, and then after this mapping, p of e given m is almost independent of n in this sense. So I have all these things out here, right? So now I'm going to, so I have all these requirements. So now I'm going to drop those requirements in this sense. Let me be precise. So this is, so I'll just say, okay, I'm going to drop the Eve requirement. And it's the same thing as before. So if I drop a requirement, the maximization only gets worse. Looser. Okay, and yeah, and that's it. So formally speaking, so what have I proved? Let u be auxiliary random variable, okay, such that u to x is something. Okay, so think of u as just m. Okay, I mean, usually auxiliary random variables are called u, but I mean here honestly speaking, u is this m. So formally, let u be an auxiliary random variable. Okay, and then I have this channel ye. So this is the channel, and this is the really speaking the encoding. So in the message encoding, we would take the uniform distribution on E on U, but now I'm even going to optimize over all U. So, okay, so as I said, maximize over all such like Markov chains. So we do this, and now an achievable rate will be less than the maximization over all such Markov chains. Class also. Markov. No, we cannot. Okay. Such Markov chain. Okay. And then it will be I epsilon min uy minus I epsilon max u. Okay. So this is actually the final converse. And I mean, when I did the achievability, there was no auxiliary random variable u, but actually you can prove achievability with this also. So maybe leave it as an exercise. So
just a question. So
yeah.
if I want to say x here, then the mapping I would take would be the identity mapping, right?
Identity mapping, yeah.
Okay.
In fact, can prove achievability with of chain requirement. So actually, like, so in fact,
but is there, yeah, I mean that strategy is pretty evident from the proof here that you just take an extra random variable at the outside and then generate
So,
a random code word
yeah.
after you have generated the code book.
Yeah.
But the point is,
So
I mean, I always see this these auxiliary random variables, blah blah blah. But do they actually give like greater rates or what? I mean,
I think there are examples known for some channels where they give greater rates. Okay.
okay, okay.
And the
So
only difference here is
explicit
that
examples are known.
yes, I mean, I'm not sure if wiretap is such an example, but specific examples of, I
Okay,
think for multi-terminal channels, specific examples.
okay.
So
But for just the point to point, so if I'm just talking about the point to point thing, we know that an extra randomization at the encoder does not help. So
for point to
there,
point, no.
for
Yes.
yeah,
For point to point, I mean, you can prove. I mean, the optimal bounds in both one-shot and asymptotic IID don't involve the auxiliary random variable. But for wiretap, okay. So I have done it at the one-shot level, but then like even in the asymptotic IID level, I mean, I can do the same thing with the auxiliary random variable. So it turns out that in asymptotic IID, the best converse known requires the auxiliary random variable. Okay, so I mean, it seems that you cannot wish it for wiretap. So I should just maybe write it there. So in fact, for wiretap, IID, best converse uses the auxiliary random variable. And then in that sense, the thing is settled that the best achievability I can get by plugging in a random auxiliary random variable u, and the best converse is matching by you plug in an auxiliary random variable u, maximize over all auxiliary random variables u, and encoding from u to x. Okay, encoding from x to y, of course, is fixed by the channel, but you are allowed to optimize over u to x. And if you're talking of computational efficiency, I mean, for asymptotic IID, you're working with the Shannon mutual information, right? So that mutual information has all nice convexity properties. So which again, I mean, we've seen before, they're just a consequence of data processing. So the problem becomes a convex optimization problem. So you can bound the size of the support of u. Okay, so if the support of x is some mod x, then size of support of u is probably mod x plus 2 or something like this. This is Kara's utility bound. It's called. Okay. So when you're doing this optimization, I mean, it is known that I need only consider random variables u whose support size is similar to that of the support size of.
wait a minute. So I might not know this. So Catherine's theorem is for convex sets with a linear algebraic structure. These are unstructured sets.
No. So the optimization is, I mean, once you fix an alphabet size u, the optimization are over probability distributions of u.
Distributions which lie in, yeah, okay, got it.
And mappings from little u to p of x.
Yeah, got it. So the alphabet size is the dimension. Okay, yeah, that's a dimension plus two.
Alphabet size is a dimension, and I mean, your domain is basically, I mean, you are optimizing your probability distribution. So you're optimizing over polytopes basically. Okay, and what you're optimizing is a convex function.
Yeah, got it.
Once you have Shannon mutual information, that's a convex function.
Right. So why do people say that these things are not computable, etc.?
Because no. In this case, they're computable. I mean, once you have a single letter thing, these are called single letter thing. There is no n here of the asymptotic IID coming in. So once you have a single letter thing, okay, then you can limit the sizes of the alphabet size of the auxiliary random variable. So it becomes definitely a decidable computational problem.
No, we have solvers for convex optimization problems also, right, which are efficient in the complexity sense, which lie in P. So
well, yeah, yes, I mean approximate solvers.
Approximate solvers, we have approximation algorithm.
Correct. But you have to bound the alphabet size, right? So Cartesian theorem bounds the alphabet size. Because I mean, u is something that you cook up, right? So a priori you can cook up u, the sample size of u to be much larger than the sample size of x. Okay. The point is that will not help you. So Cartesian theory assures you that largest useful U will have alphabet size around the same order as the alphabet size of X. Maybe it's X times Y or something like that. Okay, X times Y times E maybe, if you want to be pedantic. But yeah, something like that. So this is there in that algorithm. They will tell you what is the accurate, best alphabet size. Okay. So any questions about this group? Okay. Note
Yeah,
that again. Yeah, Hari, yes, yes.
yeah. So it's not clear to me. Like, what does it mean when we say optimizing over the Markov chain? Like, how is it different from optimizing over the distribution of X? Like taking
No,
an
Optimizing
the
over Markov
distribution of
chain means optimizing over over a joint distribution PUXYE.
yeah. Optimizing the
Oh,
Markov
I
chain
see.
means
Okay.
you first fix the alphabet size of U, okay, which by all this in the asymptotic IID case, by all these theorems, we are assured that you don't have to look at arbitrary large alphabet size. Alphabet size of U near about the alphabet size of X is good enough. Okay, so first of all, you fix the alphabet size, then you fix the probability distribution of U, then you fix the encoding. Right? I mean, think of M as U. You fix the encoding from little u to probability distributions of X conditional little. This is what you mean by optimizing over the Markov chain.
Okay.
Okay? Yeah.
So
So-
I have maybe a slightly off-topic comment. So
Hmm.
I know proofs in probabilistic method where introducing some new randomness does help. I know of such proofs, a few examples maybe, but there it's always intuitively sort of clear why that extra randomness helps. In this case, I'm just wondering why somebody would think that introducing new randomness might make sense. I mean, it seems like introducing some U, even Bob does not have knowledge of U, right? But it's
Yes.
just that Eve not having knowledge of U, this extra randomness right here seems to weaken the adversary somehow.
Somehow, yeah. I don't have a good intuition about this, but it seems to weaken the adversary. And on a different note, but still an auxiliary random variable, like in multi-terminal channels, there are examples known where, I mean, we'll do multi-terminal channels next, very next now. There are examples known where, I mean, there are these time-sharing random variables, okay, which are ubiquitous, but so you can do time sharing in the explicit sense, or you can do what is called coded time sharing, where you throw in an auxiliary random variable and use it in a particular way, which is called time sharing. Okay, so there are examples of multi-terminal channels known where the auxiliary, where the coded time sharing using the auxiliary random variable actually gives a larger region. So yeah, so I don't have a good intuition why this would happen, but this is known to happen. So, I mean, in that sense, you can see that in other contexts, auxiliary random variables do. So another comment I would like to make, see, similar to, I mean, if you go back to what we were doing about the point-to-point channel, the noisy channel, without the secrecy requirement. So remember, we have an achievability. So in in asymptotic IID, good old asymptotic IID, there was some achievability proof. We came up with a conceptually simpler achievability proof by our one-shot techniques, and then like modulo that those the second order analysis. I mean, if you treat that as a black box, which is basically a sophisticated way of doing asymptotic equipartition. So we know that you get the one-shot rate in terms of the smooth mutual information quantities. Then you take the asymptotic IID limit that approaches the Shannon mutual information quantity. So we can recover the achievability from the one-shot achievability by appealing to the asymptotic distance. Okay, but if you want to prove the converse, so converse for the noisy point-to-point channel. So there was a converse proof given in Cover and Thomas. And if you look at the converse proof, I mean, there were steps. There was a Fano step, okay? And that Fano step, usually in the one-shot case, like we cheat. We, I mean, do things like, okay, there is a decoding error, and we push that decoding error, or in this case, sequence error, into the smoothing parameter. So we sort of brush fan under the carpet by putting the errors into the smoothing parameter. So far, so good. And then we can get often very easily some converse rates like this. But these are one-shot converses. These are not asymptotic IID converses.
Yeah,
In
this got
particular,
commented last time.
yeah. So I just want to emphasize it again that if I'm trying to prove the asymptotic IID single letter converse. So single letter converse means I'll only evaluate it for one copy of the channel, not for n copies of the channel. So I'm not going to get this directly. Like this one-shot converse says that, okay, I mean, you look at n copies of the channel, treat it as a single super channel, and then evaluate this maximization over that super channel. But there's no reason why the maximization over the super channel would involve product probability distributions. Okay, I mean, why should the encoding procedure to the super channel do joint encoding? Decoding is usually joint anyway, and that's not a problem. But the problem is the encoding. Why should encoding be a joint encoding? Okay. The channel, of course, will be IID, which is asymptotic IID, but one-shot converse does not force the encoding to be IID. If the encoding were IID, then you can argue that from one-shot converse, I will get a single-letter asymptotic IID converse. But I mean, usually you cannot guarantee that. And that is why the proof of single-letter asymptotic IID converse are usually difficult. So even for the noisy channel, I mean, there was, we use a chain rule for the Shannon Mitch information, then you use the memoryless property. So these steps were there. Okay. And these steps just do not exist in the one-shot converse. So from the one-shot converse, if you want to get a single letter asymptotic IID converse, usually you have to do hard work. And we saw that in the point-to-point channel. And that was all the second order analysis, min-max theorems. And I mean, it is considerably more difficult than the converse in the asymptotic IID proof of cover and converse. But then it of course gives us more, it gives us second order rates. So at this point of time, nobody knows how to take the one-shot converse for the wiretap channel and show that it single letterizes. Okay. But independently, it is known that if all you want to do is asymptotic IID, there's a single letter converse, but you'll require to optimize over this Markov chain. So you can, I invite you to go back to El Kim and see the proof of that converse. It's an extremely complicated proof. Okay, much more difficult than the noisy point-to-point channel in the asymptotic IID. So of course the memoryless property we use, but there are all kinds of very fancy chain rules of mutual information which go under the name of this scissor sum identities, and they're heavily used there. So yeah, at this point of time, I am not aware of how one can obtain that result from the one-shot converse. So that's a topic of research. Okay, any further comments? Okay. If not, let us now move to the first multi-terminal channel. Yeah. And yeah. So the multi-terminal channel that we'll see now is the simplest one, which is called the multiple access channel. So you may have seen it already. Hari, have you seen the multiple access channel in your asymptotic IID information theory course?
No.
No? Okay, then I'll tell you. Okay. So that's called the, yeah, I mean, it's usually called the simplest multi-terminal channel now. So I mean, of course, it's simple to describe, and also it's a channel for which we have an optimal converse in the classical asymptotic IID system. Okay. And optimal single letter converse. So we will see whether you can prove analog as bounds in the one shot. Okay. So here is the channel. Here's the channel. So the channel has two inputs. Instead of one input, there are two inputs, and there's one output. Okay. So this is the channel. And so there are two senders, traditionally called Alice and Bob. So Alice has a message M that she wants to send. Bob has a message N. And these messages M and N are independent of each other. There is no, I mean, they don't come from some joint distribution or anything like that. They're just arbitrary messages. Now this message N should go through the encoding procedure. And independently Bob's message N, independent encoding procedure. So the output encoding procedure, so for every symbol, for every message N, the output will be a probability distribution over the corresponding input. And this will, I will call. So because there are two inputs, the channel has two input alphabets, X and Y, and there's an output alphabet Z. So the channel will do its work. So if the input symbol pair X comma Y is inputted to the channel will produce a probability distribution on the output symbol Z, which I'm calling PZ given Y. And this will now go through a decoding box. And then traditionally, this is called Charlie, the receiver. And Charlie's decoding box will convert the channel output into a guess of the input message pair. So that I'm calling M hat comma N hat given Z. So remember, encoding and decoding are private coin algorithms. And what do we require? Of course, there's the correctness requirement, which says that probability. So now this probability is over, like to start off with uniform distribution messages. So uniform distribution on.
Here this is different. Here you cannot say for all MN.
Yeah, so here to get nice bounds, I mean, you cannot. What Shantan is saying, I'll say in more detail in a moment, but let me write. So the probability is over the uniform distribution on the candidate messages, then over the encoding procedure, right? The two encoding procedures. Remember, the encoding procedures act independently. The messages are independent, the encoding procedure is independent. Then there is also the channel, which does something. Okay, some randomization, and then there is the decoding procedure. Right? That's also a private point decoding algorithm. So the probability over all this, that the ordered pair M hat N hat is not equal to. So I want both to be decoded correctly. So the probability that the ordered pair is not the decoder is not equal to the encoder should be less than epsilon. Okay, so this is the correctness. Okay. And the reason it's called a multiple access channel is because it was motivated by the following problem. Right. So the channel is a medium where many senders can simultaneously access. Okay, so it's a medium, let us say, like free space. Okay, and I'm doing wireless communication. So Alice and Bob are two cell phone users. Okay, and they have to communicate to the base station, which is Charlie. And the atmosphere is the channel. So Alice and Bob have independent messages that they want to transmit. So they will encode in their messages into wireless signals, that is independent encodings. And then the channel will do its work and create some noise. Okay, and what the base station receives, okay, is the output of the channel. Okay, so it's gone through some noisy process, and from the output, it has to figure out what are the messages Alice and Bob send. Okay, so that's the historical reason of the name multiple access channel. So this is the real life problem that is being modeled out here. Okay. And what Shantan said is the following. So recall, even for the point-to-point channel, noisy channel, so when we had done our achievability, we had taken the uniform distribution over the message set. Then, of course, there was randomness introduced by encoding, channel, decoding. Okay. And then we said that probability that M hat is not equal to M, okay, over all these sources of probability should be less than epsilon. So this is what is called the average probability of decoding error in the literature. And then I remarked that you can go from average probability of decoding error to the worst case probability of decoding error. Like I can ensure that every message N is decoded with error probability at most epsilon. Instead of saying that the average message M is decoded with error probability epsilon, I can say that every message M. So this was the expurgation step in the point-to-point code. And remember, the expurgation step sacrificed the rate. So, I mean, we sacrificed 1 bit in the rate, and the epsilon became 2 epsilon or something like that. Okay, but one could ensure. But unfortunately, you cannot do the expurgation step for the multiple access. The reason is not hard to see. The thing is, if you try to do an expurgation, surely you can say that for most message pairs m comma n, the decoding error is less than 2 epsilon. You can say that. Okay, so you can say that for 90% of message pairs m comma n, the decoding error probability is less than 10 epsilon. So far, so good. But you cannot guarantee that these 90% messages form a rectangle. Okay, so rectangle means, let me write on that. So average decoding error is essential in this problem. Reasonable rates. Okay, so expurgation step does not work because 90% of common error having error less than epsilon does still. So what do I mean by this? A rectangle is basically a set of m comma n, which is of the form something Cartesian product sum. So like does not give a rectangle. That is the good m comma, the good set of m comma n is not of the form m prime times m prime. Okay. So remember, for the point-to-point case, what we did, we found some good messages, and we said 90% of symbols m, message symbols n have decoding error less than, okay, should say, by 10 times epsilon. Okay. So, and then I said, okay, just restrict your attention to those ends. That's the expurgation step. But here, what we want, remember, Alice and Bob should be treated independently. So the set of allowed good messages of Alice should have nothing to do with the allowed good messages of Bob. So in other words, I'll be happy if I can say, oh, fine. I mean, I don't want to transmit all the possible messages that I was doing earlier. I'm happy to transmit a subset n prime of messages. Bob says, I'm happy to transmit a subset n prime of messages. But the expurgation step will give you a 90% set, but that is not of the form m prime times n prime. Okay. In fact, let us say all the diagonal messages. Diagonal messages mean message pairs of the form m comma n. Let us say all the diagonal messages are bad. So the fraction of bad messages is very small. I mean, the sub-constant fraction of messages are bad. Nevertheless, there is no large rectangle out here. Okay, there's no rectangle out here among the set of good messages. So these kinds of pathological.
There is a rectangle, but that rectangle is very small. That's all.
Yeah, very small. Yeah.
You,
So
you have
to get
to
reasonable lengths.
you have to take a rectangle which is like above the diagonal, which essentially
Yeah,
misses
above
out
the diagonal.
50%.
Correct. Yeah, you have to take a rectangle which is above the diagonal, but that is very small.
So I mean, maybe I'm repeating what Pranav said, but essentially the point is here that you cannot sort of take a subset of messages on mn, the subset mn, which looks like it's not uniform, which looks like it's a peaked or a biased distribution. Any safe subset of messages that you take, that has to look uniform to both Alice and Bob on the marginal, and that cannot be done because of this property that just Pranav said. Expurgation is fine, but maybe you're expurgating some random slice of the rectangle, and then you're screwed.
Yeah, maybe I mean, think of the diagonal example. Maybe I mean your things that you're expurgating are kind of like a diagonal. I mean, there is like every like either every n gets affected by a bad pair or every n gets affected as a bad pair.
Okay, in fact, I have one more comment. So in El Kim, this might help. In El Kim, there is an exercise in the Mac chapter, in the multiple access channel chapter, which sort of gives you an explicit example of a case when the expurgation actually takes out a bad part. And I think it essentially leads to product example, but it's a nice exercise, and
Yeah, it's a nice exercise.
It's due to somebody called Duart, if I'm not wrong.
Yeah. So yeah, I know there's an exercise. Yeah, so I think it's a good thing to do. Right? So Hari, I mean, you should probably go back now and read the chapter on the multiple access channel from El to get the background. Okay? So and understand why expurgation, I mean, is not good, because I mean we don't get this. Okay. So I think we will stop here. I mean, though we began late for various reasons, but yeah, I think this is a good place to stop. And since you haven't done the Mac before, I think it's good you understand what is known about the Mac in the classical asymptotic IID. Okay, and then next time we will take up the one-shot Mac. Yeah. Any questions?
I had a question about the course. Like, how is the grading policy and all?
Yeah, grading. So okay, so I'll send out some assignments. So yeah, so you're taking this for credit, right?
So I have not decided actually. The drop deadline is 18th, so I was waiting for the assignment and then decide.
Oh, for the assignment. Okay. Yeah. So drop deadline is 18th. So maybe I should send an assignment in a couple of days, and so it will be basically based on the assignments. Okay. And I mean, I think there's supposed to be final exam, but my final exams will be take home. So usually you should probably ask Shayan then. So I like to give assignments which make you think. The correction will be lenient, but the problems will make you think.
So the problems are hard, but they are always broken down into very nice little steps, and you are allowed to look at the net and ask
You're allowed to look at
other
anything.
people. You're allowed to look at
Anything
anything and talk to
in the
anybody,
world.
as long as you mention it explicitly in the. So you're allowed to talk to me also, because I mean, and in fact, if I am not available, you can always sort of mail Pranab and ask for hints, or you can ask me as well. You're allowed to do those things, as long as you sort of mention and understand the thing yourself, then it's cool.
Yes, I mean, you have to tell your sources, but yeah, I mean, you're highly encouraged to ask for hints in this.
Yeah.
These
And
things are normal.
in fact, Pranab's problems, you have to ask for hints. Okay, you have to. I mean, there is, especially if you're inexperienced, you have to ask for hints. But I mean, this course is Pranab is sort of more chilled out than I would say other people, so it's fine. And the grading is very lenient.
The grading will be, the corrections will be lenient.
And that I can tell you right now. I mean, even in front of Pranab, the grading is super chill. So.
Yeah, and I mean, usually, I mean, Google search will not help you.
Yeah.
You can try anything in the world you want. It will not help you. Okay. So yeah, I mean, sometimes maybe, but I mean, averaged over all the assignments, Google search will not help. Even I gave qualifiers which were open book.
Yeah. Hello. Here. I'll tell you
Nothing
something.
will help you.
So in my qualifier, Pranav essentially solved a new problem, an open problem, and he gave that to me as broken up steps. And I didn't know that was an open problem, but I did it. I solved, and then after the exam, he comes and tells me that that problem was open. What? That actually happened. But it's doable. It's very doable. Once you get used to things, it's very doable. It's just that you have to build some intuition. That's all.
Okay, so I'll stop the record.